into this university lending system, and we then have our possible things that are in this lending system. For example, first of all, let's look into this. This is how this looks, and there are different design choices that were designed. First of all, you might go into the user story that we already know. These are different user stories, and the code we already talked about it. The code, we know these user stories: time selection, borrowed books with email address, high demand genre, overdue book tracking, free up library space. So all of this we already know. Then we might go ahead and look into the entity relationship model design. So student is an entity because we need to store and look up student info, for example. So student ID, name, email on its own are separate from one loan. For example, borrowed books with email address and overdue books tracking both need student details attached to a loan. So student is an entity. Book is an entity because its properties, for example, book ID, released year, total number of pages, title, language, describe the book itself, not a specific copy or a specific loan. Almost every user story needs this. For example, showing the book title and borrow count, or listing books with their copy count. So these are user stories that needed this book entity. So author is a separate entity, not just a text field inside book, because we need to count and rank authors on their own. For example, which author books are borrowed the most, or authors with books over 200 pages. That's only possible if author has its own ID and can be grouped by. Then we have genre as a separate entity. For the same reason, we need to group and count by genre directly, because that's also based on user story, like finding the most borrowed genre, or students who borrowed from at least 3 different genres, or the top 5 books per genre. That only works if genre is its own table, not just a label on book. Then we know that copy is a weak entity linked to book. Instead of storing copy details inside book, the reason is simple: it's the physical copy that actually gets borrowed and returned, not the book title itself. That's why instead of storing copy detail inside book, we have a separate thing called copy, and it's a weak entity because book copy is dependent on book. It cannot live on its own. That's why it's very weak. One book can have several physical copies, each with its own edition and ISBN, and we need to count how many copies each book has. Since a copy doesn't make any sense without knowing which book it belongs to, copy numbers reset at 1 for every book. It's not that, okay, 1, 2, 3, 4, 5. This resets. This again goes to 1, 2, 3 based on every single book. It's not the same copy for every book. So that 1, 2, 3, the copy is the same, but for book A, 1, 2, 3, that's fine. But if we had no difference between this and a new copy, we need to have a difference. Otherwise, it will just continue 4 for the same copy, A, 5 for the same copy. But wait a minute, this is actually not the thing. We now have B, and for this we need to start from the beginning, 1, 2, as a separate copy, not just going 1, 2, 3, 4, 5, because we have a different copy ID here that has different number of copies. One book can have several physical copies, each with its own edition and ISBN, and we need to count how many copies each book has. Since a copy doesn't make sense without knowing which book it belongs to, copy number resets at 1 for every book. Copy is a weak entity with a composite key, book ID and copy ID. These are the two that we use. Book has author is modeled as 1 to many or 0 to many relationship. This is resolved via book author bridge table. A book can have multiple authors, and an author can write multiple books, so this can't be captured with a single foreign key on either sides. This supports queries like which author books are borrowed the most, for example. Then book has genre is modeled the same way: 1, many, 0 to many. resolve via book genre table, because you have many to many relationship. You cannot join this without another extra table. So that's what we did here, and that's what we did here too. Since a book can belong to more than one genre and a genre swaps many books, this supports queries like most borrowed genre or top 5 books per genre. Book has copy is a 1-to-1 zero to many relationship. Every copy belongs to exactly one book, while a book can have 0 to many or many copies. This lets us simply count copies per book, no bridge table needed here. Then we have student borrows copy is a many to many relationship here. Relationship with its own attributes. Borrowing is the new table that connects to specific copy, not the book. What actually gets borrowed and returned one physical copy item, not the abstract title. So fields like borrow date, return date, due date, fine amount, and paid describe facts about that one borrowing event, not the student or the copy in general. So they belong on the relationship itself. This is what makes it possible to check which loans are still unreturned, how many books were borrowed in a date range, or who currently owns a fine. Then we have a ER model. In this ER model, we can see this is a strong entity. Then if we convert into relational schema, we write this and its attributes, because every entity gets a table and then its attributes, because this is many to many here, and we make a separate table for this one, borrows, that has all of its attributes. But because copy is a weak entity and of book, so it's a weak entity of book, then we take this and we put it in this, and then copy has its own table with its own attributes, then book has its own table with its own attributes, and this then many to many creates a new table here. But because there is no relationship of weak or strong in this case, then we simply just in the new book author table only give the key of book ID and author ID. That's the two things that come in this new book author table as a relational schema. For book ID is selected as the primary key. Title was considered as possible natural key but rejected. The dataset itself shows several books sharing the same title. For example, 2 different editions, both titled The Metamorphosis. So title alone cannot guarantee uniqueness. That's why we needed book ID. For author, the same reasoning applies to name. 2 different real authors can share a name and there is no guarantee of uniqueness. So author ID is introduced as a surrogate primary key rather than relying on name. For genre ID is used as primary key, since genre names, while usually distinct in practice, are short labels that are better referenced by a stable numeric key than repeated as text in every related row. For student, name alone is not suitable as a primary key, since multiple students can share the same first or last name. Email is a candidate key, since it is expected to be unique per student, but email address can change over time and have a more complex structure than a simple identifier, so they are not well suited as a primary key either. An additional attribute, for example student ID, is therefore introduced, which is assigned uniquely and used as a primary key. Copy is treated as weak entity, which is dependent on book rather than just an independent relation. A physical copy has no identity of its own outside the book it belongs to. Copy numbers are only meaningful per book. For example, copy 1 of book A and copy 1 of book B are 2 different physical items. The primary key of copy is therefore the composite key. So book ID plus copy ID is used in at the same time, where book ID is inherited from its owning book relation and copy is partial or discriminating key. Then we have normalizations, where first normal form first NF is satisfied. Every relation holds only one single atomic value in each column. Single valued attributes and the potentially multi-valued relationships book to author, book to genre are resolved through separate bridges relations rather than being stored as repeating groups or comma separated list in a single field. Second normal form is also satisfied. A relation is in second normal form if it is in first normal form and every non-key attribute is functionally dependent on every candidate key, not just partially dependent on part of a composite key. Relations with a single attribute primary key, for example student, book, author, genre, automatically satisfy this since there is no part of the key. There is no part of the key for an attribute to depend on. For the relations with composite keys like copy, book ID plus copy ID and borrows, the remaining attributes were checked against the full key. For example, condition in copy genuinely depends on the specific physical copy, not on book ID alone. Two copies of the same book can be in different conditions, so there is no partial dependency here. So we need to make sure in second normal form there is no partial dependency. For example, that and every non-key attribute is functionally dependent on every candidate key, not just partially dependent on part of composite key. So it's not that only just the part of the composite key it's depending on, like the copy ID. It needs to be depending on both complete key. It needs to be fully functionally dependent on candidate key, not just partially dependent. And there is no partial dependency here. So 3NF is that the functional dependency between non-key attributes were examined. In borrower's relationship, a problem was found. Fine amount can be calculated directly from due date and return date. A late returns produce a fine proportional to the number of overday. This means fine amount is functionally dependent on other non-key attributes. Like it's not even a key, it's just an attribute, but this is dependent on another non-key attribute, which is not third normal form, rather than being an independent fact tied only to the key, which technically violates third normal form because the following two main reasons we kept it. Audibility, because fine amount and paid together form a financial record. In our history we know that this is a physical thing that is recorded, we can keep it. Storing the value preserves fine as it was actually charged, even if the rate changes later in the future, we have a history. Or the librarian manually waives the fine or adjusts, or a purely computed value would lose the history and would always fall back to default formula. Recalculating the fine every query is slower than reading. The second reason is performance, especially since borrowed is frequently joined and queried, like list, etc., etc. We already know how the relational schema was created. We talked about it. We know student to copy has many to many relation, book to genre has many to many, book to author has many to many, and book to copy has one to many. Then we know that design choices on SQL query, this is something that doesn't really matter. These tables don't matter as well. These queries are something that we have already looked into. Then the only thing that's left is reflection. The database design is built around three main areas: book inventory, lending policies, and circulation tracking. Each area uses a normalized structure that avoids duplicate data while keeping the records accurate and consistent. Then we have book inventory. Books and physical copies were kept as separate tables. Book stores information about the title itself, the title, released year, total number of pages, language, while copy represents each physical item on the shelf, that is there on the shelf. Using a composite key, book ID, copy ID, this split is necessary because whether an item is currently borrowed, overdue, or available is a fact about one specific copy, not the book in general. Storing only a copy count on book would make it impossible to track individual items. Since a book can have multiple authors and belonging to multiple genres, these relationships were handled through two junction tables, for example, book author and book genre. Storing a single author or genre directly on book was not an option, since it can't represent co-authored books or books that fit more than one genre. Then we have lending policies, where we say the borrows table stores each loan details: borrow date, due date, return date, fine amount, and paid. One key decision was to store fine amount directly instead of only calculating it from due date and return date. This isn't fully by the book for normalization, but was chosen for two practical reasons. Financial records need to reflect the actual amount charged even if a fine is later waived or adjusted, and looking up for a stored value is faster than recalculating it every time the report is run. Another rule is that making sure the same copy can't be borrowed by two students at once couldn't be enforced with a simple unique constraint, since the same copy is borrowed and returned many times over its life. Instead, a trigger checks for an existing active borrow, that is it even already borrowed, before allowing a new one to be inserted there. If someone wants it, if it's already borrowed, then it will not let it happen, but this is what it checks. This query will check, and this is all possible because because of the way we did the overall design. Circulation tracking. Because the schema was normalized from the start, most reporting queries grouped by genre, author, or borrow count came together easily through simple joins. The trickier part was correctly checking whether a copy is currently borrowed, since there is no stored status column for it. Preventing the same copy from being borrowed twice also needed a trigger than a plain constraint. Since MySQL does not support unique constraints that only apply to active rows. Now we can see that there is this joins before and after. We can easily see how joins are working here. For example, we have two base tables used, for example, suppliers and supplier ID. For example, suppliers and contacts. These are two different tables. Suppliers has supplier ID and name. Contact has a contact ID, name, and supplier. Then we know why does your example table matter, because with perfectly matching data, inner, left, right, and full all return the same rows. The difference only shows up in unmatched rows on either side. That does not match. That's the difference that happens. For example, inner or natural join, select all from suppliers table. We make it a variable. We say join contacts. So we contact this, we join this with this on supplier, this table, where this supplier we match. Join means to match. This match this with this, and wherever this matches with this the same, for example here it matches the same, here it matches the same, we get this in our resulting table. This like this, like over here, and this like this over here. Perfectly fine. Then what happened? Only pair where join condition matches survive. Venus, HE, and no contact, and Lena supplier 4 doesn't exist and are both dropped. They are dangling tuples with no join partner. So what does join alone mean? Join defaults to inner join. The word inner is optional. It's just optional, but it's just a join, normal join or inner join. Left outer join. What it does is that it selects all from suppliers, left join contacts on c.supplier supplier ID. We are doing now a left join. Now we say that on the same table that we had here, now we have the second example same. So what happens is that then we look at inner join. We already saw the inner join or the natural join or the normal just join, and we know how that works. Then we look at left join or outer join. So select all from suppliers, where we do left join. It contacts C. So between contacts table and suppliers table. From suppliers table, join it to contacts, where supplier equals to supplier ID. So supplier ID this and supplier ID here. So sorry, supplier here, this supplier from C contacts. So then what's gonna happen is that it's gonna see the matching ones. Of course we have this match and this matches, and then we put it like this. This goes here, the entire row like this. This one, because it matched, this it's also matched, it comes just like this over here. But what about those that did not match with this supplier and supplier ID? 3 is not the same as 4. we still only write the left one because it's a left join. Only write the left one, the left part here, just like we did, but the remaining of this one we put null. So on the right outer join, it's also outer right join, what happens is that we see the match supplier, this is supplier ID, and this is not the same. But for now, because it was a right join, only the right information comes. So this goes all the way here. Like normal matches are untouched, but things that do not match, like this and this they do not match to each other. We check the supplier with supplier ID, and when they did not match, what happens is that the right one comes, like this comes as it is because it's a right join, this comes as it is, but this one becomes a null here, you can see, and this one comes as it is, right side comes as it is. Then we have full outer join. Again we check on the same condition, supplier ID, target this, okay, these two are same, then we know we need to close our eyes and just put this as it is here. 1 2 are coming as it is. But what about the 3 now? Because 3 is not same as 4. This actually is the combination of left join plus R join. So one time we put the information of 3 and keep all the other null. For the first we put a left join, and then we apply the right join afterwards, and then we put this null of this side, this side, and then we put the information here like this. This is a full join. It's called full outer join. That's what it's called, full outer join. This is also outer, this is also outer, but these are left, right, and this is full. Then we have implicit join. Select all suppliers where this is equal to this. So before the to output, what happens is that we know where supplier equals to supplier ID. So let's see the similar. Now what happened semantically, the from clause from the Cartesian product 3/9 candidate pairs, then where keeps only the pair fulfilling the join condition. The result is identical to the inner join, and the database management optimizes an efficiency join strategy instead of actually materializing into 7 pairs. So it only gave us something that was the same, that matched. So 1 2 came here, Omar 10 came here, Carl, and this 2 came here, and everything else is gone. So we know that where this equals to this, no condition, no saying joins or something, from this and this, where this equals the same, and that's true, like this equals this, right? It performed a Cartesian product, and then it's very similar to the inner join. And that was it about joins. Then we move forward towards seeing how to read a notation. In min-max we read left to right, in Chen we read right to left. So if we have a student and card relationship where a student owns at minimum one card, at max, so a card belongs to at minimum one student, at max one student, or a card can be owned by one student. Then to convert this into min-max, we take the maximum out, this one, so we write 1 here, we write 1 here, we also take max, and then we flip the side, we put this one there in the final output, and this one here, other way around. That's the Chen. And then here we do the same thing. Professor, a class belongs to 0 or many professors. A professor teaches in is one at least one class. Then we take only this one, we take many here we take one class. Then what we do is that we put this many on the other side, like here. Like generally speaking, this is how it was, many to 1, right? Many, we had many like this, and we had 1. Then we flip the side, we said 1 comma many. This is how we do it, converting into Chen notation. For this we also select we just simply write it like this, n and m here, and then we put the n on the other side of, we put first it doesn't really matter because it's many to many. Even like to be fair, we put it other way around like this, but on the both sides it's many, so it makes no difference. That's the real solution, because we have to convert every time. Then we can see, okay, before put the foreign key on the one side. Imagine we have a situation where we have like this. How would you join these two tables? You take the foreign key of many and you put it in the one table, where you had this in the max side, like 0 to 1 or whatever, but many, this many needs to go in this table. Here you join one to many, or even if it was 1 to 1, then you still put it somewhere based on the logic. For example, there is a table called student and there is a table called ID card. There is no link yet. Student ID we have, name we have, ID card we have, and it's valid until. After ID card absorbs the detail, we use student ID as a foreign key in a new table, and then we say valid until and IN card. No new table is needed. One side gets the other key as foreign key. Unique enforces at most one of one, prefer the side with mandatory participation, minimum 1, so no null appears. Could you merge two entities into one table instead? Yes. For 1 to 1, both direction total, there is a legal alternative. For 1 to many, foreign goes on the many side. So if we had 1 to many like this, like on one side, on the other side we have many, so many goes on this side. Sorry, the foreign keys goes on my before the professor, the one. So we have Sprick, we have Kistowski, only one professor teaches one course. Then we have class ID, and we have the title they are teaching. Then we have class ID, for example, database 1, then we have software engineering 1, then we have TCS. Then we have title that they're teaching database. Each class stores its professor. Then we have this as a foreign professor, as a professor ID as a foreign key in this new table. You can see this came here as a new table, and title came here with the class ID. So this stayed, and we use a foreign key in this new table. So this already stayed as a primary key in this table, and we joined it. But if one table shares the same primary key, we don't have to join them. Or we can join two tables that share the same primary key. So the one side key migrates into the many side. So the one side went to the many side, this went to this, and once that happens as a foreign key, so this will be a foreign key. So it's the other way around. One goes into the many side, so the one side goes to the many side, teaches many subjects. So one goes to many like this, where this one becomes a foreign, the primary key of one becomes a foreign key in many, the new table that we make. So why not a separate relationship table for one to many? Allowed but unnecessary. The foreign key column does not job without an extra join. We have many to many new table with composite key from both sides. Before we had students, before we had class, we had student ID, we had name. This is the primary key here, this is the primary key here. What we do is that we take these two because they had many to many on both sides, and we make a new table for it. Neither side can hold a single foreign key, and we know this is pretty much the same rule. Then we have normal forms: first normal form, second normal form, Boy Scout normal form, and fourth normal form. Only atomic values. So multi-valued phone column violates, for example, many phones numbers in just one. So make a new table for it if you want to add multiple phones with the same ID here. And then no partial dependency on part of the key. Before, primary key is this, but name depends only on student ID. So name here only depends here. This is not okay. We need to make a separate table where name depends fully on the student ID, because this name does not depend here. It doesn't matter what class ID he has, name only depends on student ID. Then we create full dependency by saying student ID we give here, and we say student, and we say class, and then we say grade. Now we have full dependency of student ID, because you can see that name depends only on student, but now name depends on the full table depends on it. So you can see this depends on this depends on that, which was not the right way to do it. Now we know that we have created full dependency. Mass was stored once per enrollment redundancy and update anomaly. Attributes depending on only part of a composite key. So this is a composite key, right? And in a composite key, 2NF is only in a composite keys. So in any composite key, if the name is only depending on this, then this is a problem. Name must depend on both. In this case, it depends on both, because now we have student ID that goes to this, and then we have a grade. So we distributed the table further, because attributes depending on part of to their own table, 2NF is only ever an issue when the key is composite. So if the key is composite, only then we have to care about second normal form. Then we have third normal form, no transitive dependency via a non-key attribute. So we know that this depends on this depends on that, this depends on that. This is not fine, because these are depending on a non-key attribute. So office hangs on professor, not on the class. So after making it the third normal form, we get this, and we say okay title, and then we say a foreign key this, and then afterwards we give the same ID here, and we make a new table for professors, and we break it into two tables, so that this depends on key and this also depends on key. So was duplicated because it depends on professor, who depends on a class, a transitive chain key, non-key goes to non-key. This is not okay. We cut the chain. Everything that hangs on ID moves to the professor. Then we have BCNF. Every determinant must be a candidate key. So functional dependency is a class ID goes to tutor ID, and tutor ID goes to class ID. Each tutor tutors exactly one class. So before in third normal form, but tutor ID is a determinant, not a key. So tutor ID is a determinant, it's not a key here. So after, what happens is that we know that if there's a determinant, it goes directly to the key. After that, there are two keys like this. So the fact that T5 tutors T5 tutors this was repeated for every student of T5. Third normal form tolerates this. Class ID is a part of key. Because class ID is part of a key, Boy Scout normal form doesn't. The left side of every functional dependency must be a candidate key. So we know that for example, tutor ID goes to class ID, violates that. So tutor's class assignment gets its own table. So then what happens is that we make a new table called tutoring, and we say okay, class student ID is here and tutor ID is here, and class ID gets its own table where it then goes to tutor ID like this, because tutor ID is a determinant, it's not a key. And if it's not a key, third normal form in one sentence, BCNF drops third normal form exceptions for attributes that are part of some candidate keys. For example, it's strictly trigger, and the decomposition may no longer preserve all functional dependencies. So for it does not preserve any functional dependency. For example, this is a non-key candidate key, but still it cannot depend on this. We can make a separate table of only these two, only this and this over here. So it clearly depends on just one key. Then we can say it here, and this as a non-key attribute comes here. So fourth normal form, no independent multi-valued dependencies. We have multi-value dependencies like professor ID, class, professor ID goes to language. Classes and languages are independent of each other. So before Boy Scout normal form, all keys no functional dependencies but store the cross product. For example, professor ID, class, language. So after it teaches, after what happens is that we take teachers table where we put these two things together, and we say language and professor ID here. we know that professor ID is a primary key, so we keep a primary key and we use it. So this is dependent on that. So two classes, two languages, forces, 4 rows, pure combinational redundancy. Also, there's no functional dependency at all. The whole row is the key. So BCNF is satisfied. Two independent one-to-many facts about the same entity must be stored in tables. So given a BCNF not in fourth normal form, the tail sign is that an all key table whose row count is a product of two independent lists. We can just say it out loud that, for example, min max, keep the max values, swap them to the opposite side. Functional dependencies on one side plus unique, this is one-to-one. Mandatory side preferred, what's mandatory is preferred. Functional foreign key goes into the many side of the table. Of the one's foreign key goes to the many side. New junction table is made for many. Composite key, we use primary key plus foreign key in this new table. First normal form is atomic value only, no lists repeating groups. Second normal form is no attribute depends on just part of a composite key. Third normal form is no transitive dependency, key goes to non-key. So that's not. Boyce-Codd normal form is every determinant is a candidate key. So everything that determines something is a candidate key. Then we have fourth normal form, no two independent multi-value facts in one table. Topics that are left is Boyce-Codd normal form and fourth normal form. So database anomalies, let's break down the Boyce-Codd normal form and the fourth normal form. So the key symbols, this is our primary key, this is a star is a foreign key, and just this is a regular attribute. Then we have Boyce-Codd normal form. So a table is in BCNF if every determinant is a candidate key. So if column A determines column B, A is determining B, then column A must be a super key or a candidate key. It needs to be a candidate key. It cannot just be an attribute. The problem before BCNF. Imagine a college database tracking students, the subjects they take, and their professors. So we have a student can take multiple subjects. Rule number 2, each professor teaches only one subject. So student can take multiple subjects, like many. And each professor teaches only one subject. So the composite is, we need composite key. We have student ID and we have student subject. That's what. So this is the primary key. This is the primary key. We have student ID. We have subject. Student ID. We have subject. And then we have the professor, which is an attribute that repeats. This violates Boyce-Codd normal form because each professor only teaches one subject. So each professor only teaches one subject. Because professor determines subject. However, professor is just a regular attribute, not a candidate key. This causes redundancy. Dr. Smith name is repeated alongside. So you can see that Dr. Smith is repeating because it's just a normal attribute depending on a foreign key. So the solution, what happens is that to fix that, we split the table into two. We isolate the anomaly causing dependency into its own table. So we first see if there is anomaly repeating. For example, student professor maps which student is paired with which professor. We have composite key and a primary key. So professor is a primary key and foreign key, and student ID is primary key, and then we use it to make a new table. And then we have another table that maps to specific subjects. For example, professor, this is now primary key that goes to this subject, this subject, this subject. Subject goes to this. So this was basically our Boyce-Codd normal form, where each professor can now go to a specific subject, and a specific professor is in table 1. Each professor is paired with each maps which student is paired with which professor. So this professor is paired with this student, this professor is with this student. So we have a primary key professor, but in this table it's a foreign key. It's actually primary key of another table. If we put it here, then it becomes foreign key. And then we make sure that attribute is clearly depending on a key. But even here a attribute was depending on key. That wasn't the real problem. The real problem was that it was not a super key that was depending on it. So we need to make sure it's a candidate key. Now we know it's a candidate key. Physics is a candidate key, calculus is candidate key, calculus is candidate key. This candidate key goes to a primary key. Then we have a fourth normal form. A table is in fourth normal form if it's in Boycott normal form and has no multi-value dependencies. A multi-value dependency occurs when the presence of one or more rows implies the presence of one or more other rows in the same table. For example, imagine a database tracking employees, the project they work on, and the hobbies they enjoy. Project and hobbies are completely independent of each other. Composite primary key, all columns, Empfehlungs ID, employee ID, or project hobby, because no single column uniquely identifies a row. So no column identifies a row. This is a row, this is a row, this is a column. So no single column uniquely identifies a row. Why this violates fourth normal form? Because employee has two projects and two hobbies. Because the columns are independent but cramped into one table, we are forced to represent every mathematical combination of their projects with hobbies and add third hobby and insert two new rows. This is a multi-valued dependency where employee ID is dependent on project and project is dependent on employee ID, and employee ID goes to the hobby. The solution: we make composite key. We make a new table where we make a composite key of employee ID and project as primary key, and we keep it there. Then we have a second table where we say employee hobbies table, where we have employee ID and hobby. Here we have these two combined as a primary key. Now if employee picks up a third hobby, you need to add one row to the hobbies table completely independent on their project.